Thanks for joining me. I'm Letizia. I'm from Alphawave Semi. I'm VP of Product Marketing, and I will talk a little bit more what we did with Keysight on the UCIe silicon validation and silicon results. Okay, so a little bit about Alphawave. For who doesn't know us, we provide leadership in connectivity, IP, and custom silicon. So we develop high-speed SerDes IP, like 100 gig, 224 gig. We also work on memory IP and UCIe die-to-die interconnect. We also use this technology for custom silicon in chiplet. We actually are proud to announce, and we announced last week, our first I/O extension chiplet based on UCIe connection and enabling PCI Express and Ethernet extensions. Other things we do connectivity product. We are based on our PAM4 SerDes IP, and we do provide optical coherent product for next generation networking. Okay, in terms of chiplets, let's talk about it. There was a lot of discussion in the last years when chiplets are coming, when we're going to use chiplet. The time is now. Everyone doing design today is using chiplet. If you're not doing it yet, you're going to do pretty soon. There is not enough anymore a silicon that we can put in one single SoC. We need to break it down in multiple parts. So there is different way of doing it. And especially with the AI, we are seeing more and more introduction of chiplet in the market. What chiplets are, they are multiple die in a system in package. And you start creating this big high wave of signal going from one die to the other die that needs to be interconnected with very high speed and reliable signals. Okay. In 2022, we see the introduction of UCIe, Universal Chiplet Interconnect Express, that defines standard for die-to-die interconnectivity. You will see in the next slide some more details about what UCIe is and how it gets used. Here we go. So UCIe defines a pretty layered approach to die-to-die interconnect. We start from the physical layer, where you implement all the word receiver, transmitter, the clocking. Then you have a die-to-die adapter, where we implement CRC, retry, and parameter negotiation. And then you have, like in PCI Express and CXL, a protocol on top. UCIe specifies PCI Express and CXL over the die-to-die link, or you can have a vendor-specific streaming protocol controller. At Alphawave, we implement UCIe multiple technology nodes, both TSMC and Samsung Foundry. And we also implement different test vehicles, being test chip or I/O chiplet, for creating interoperability platform and validation. Here we go, how UCIe supports all different types of package and form factor. You can have a system in package in organic substrate, classic organic package, or you can have UCIe in advanced package like silicon interposer, embedded bridge, or RDL interposer. UCIe allows you to have a different type of form factor. So for standard package, there is by 16 or the by 32, stack by 16, mainly used for organic substrate. Or you can have advanced package with by 64 or by 32 module. You can see that advanced package take advantage of very fine bump pitch. It's around 45 micron, where you can get really high density wires. We're talking about 10.5 terabit per second per millimeter, while standard package take advantage of classic C4 bump. 130 is the state of art as of today, where you can get around 0.9, 1.8 terabit per second per millimeter. This picture not really up to scale, but standard package is really wide and long. Advanced package is really small. No questions? Let's go ahead. In terms of design challenges, when we design this type of IPs, they can simply be simpler compared to high-speed SerDes, but they have other type of complexity. First of all, you want an IP that is really simple and your power gets really efficient. And for doing that, you need to make sure to balance system complexity, circuit complexity, with really high efficiency design. The power supply is also really important. You cannot put so much voltage regulation inside this IP, otherwise you're gonna really over-design what needs to be really simple. And also the architecture needs to be flexible. We need to support different type of package, different type of bump pitch, different type of clocking. So you need to have an analog library IP that can be composed in different type of form factors. Here, some of examples. So let's look at standard package, where we have our organic substrate that connects two die 1 and die 2. This is an example of a package design where we have transmitter, receiver, design routed to the other die. In this type of system, we have a terminated 50 ohm type of connection, and the bump pitch is around 120 micron with a length based on the standard, based on the package type, around 25 millimeters. To be really UCIe compliant, you need to be fitting an insertion loss and a crosstalk mask based on the standard. You can see that it's really important to design the package correctly to have the eye opening, vertical eye opening, horizontal eye opening within the standard. And these are the results from our 24 gigabit per second design. Another example of routing study is based on CoWoS-S, silicon interposer, TSMC technology, or CoWoS-R, RDL interposer, also from TSMC. In this case, you can see the wires are really, really dense. With 45 microband pitch, we can have 64-bit TX and 64-bit RX, really routed in really small space. It's really important to balance the power and ground routing across all the layers. And in this type of package, we have termination is open, pitch is around 45 micron, and the length is really short, 1.52 millimeters. When we are in this type of system, the challenges for CoWoS type of package is really maintain insertion loss and balance for crosstalk. So you can see a lot of ground shielding between the traces. Now, with Keysight, what we did, we built up a methodology that used signal and clocking jitter and noise impairment, as well as all the analog front-end linear filtering. We create our IBIS AMI model, and in collaboration with Keysight, we build a performance validation for our 3 nanometer UCIe IP. And we designed that both for standard package and advanced package. Here's our silicon results. This is the first in the industry, real 24 gigabit per second UCIe IP. This is our standard package. You can see the two little die in around 22 millimeter traces from one die to the other die. This IP is compliant with the latest standard, the UCIe version 1.1. Includes all the circuit required for electrical PHY, logical PHY, and PLL. And you can see a really nice, beautiful open receiver eye up to 24 gigabit per second. Other important things when we do this type of IP is to be able to read the receiver eye on the die itself. And in this picture, you can see the picture from the receiver side, where we have the receiver non-destructive eye at 24 gig. And this shows you 16-bit running at the same time and the eye opening, both vertical and horizontal opening. On the same side, you are able to reconstruct the transmitter side, still running at 24 gigabit per second. I talked a little bit about UCIe bump out and form factor. Here is a little bit more about the architecture that we are planning to deploy for 32 gigabit per second. It's really important to have this architecture is scalable from 24 gigabit to 32 gigabit per second. And what we allow to do with the UCIe is to use same type of clocking and then able to scale up to 32 gigabit per second. Here are some first results that we have on our 32 gigabit per second IP, done both on advanced package and standard package. We are able to still meet the UCIe spec for crosstalk and insertion loss. And you can see with all the impairment of the link to still meet the eye opening based on UCIe. In summary, Alphawave, we do have a UCIe IP, but also we use the same methodology in terms of system level modeling and silicon correlation, also for all other rest of IP. Definitely, there is more complexity when we talk about PCI Express Gen 7, PCI Express Gen 6, 112 gig SerDes, and 224 gig. All this IP needs to be validated on silicon, so we do have experience starting from 7 nanometer, 6 nanometer, down to now designing for 2 nanometer, and moving definitely next, what is the technology is going to offer next. So we are ready definitely, and thanks to the Keysight partnership, to enable next generation of 32 gigabit per second UCIe dead-to-die IP. We do create pre-silicon and post-silicon platform for interoperability of the UCIe IP. And we are committed to partner with Keysight and also our customer for success. And I strongly think collaboration is crucial to enable end-to-end interoperability and solution for the next generation of these complex systems.